Johnny here with Simpson Math. In this video, we're going to be talking about angle measure. There's a lot of vocabulary and terminology in this video. In an upcoming video, we'll be defining the trigonometric functions. But in order to do that, there's a lot of vocabulary that we first got to be comfortable with. So I'm going to start off with some symbols that you should maybe remember from a geometry setting. So if you see a line with arrows on both ends, meaning that line extends left and right forever, we call that a line. That symbol means a line to us. Instead of arrows, if we had little endpoints, little dots, do you remember what that's called? We call that a line segment. And then if we kind of put the two together, I'm going to have a endpoint on one side and an arrow on the other. So it ends here, but the arrow will extend to this right direction forever. We call that a ray. All right. In order to create an angle, to have an angle, or to physically draw an angle, we're going to start off with a ray. So I'm going to talk about how to create an angle. To draw an angle, or to create an angle, we draw a ray first, and then we rotate that ray about that endpoint. So to draw an angle, we're going to draw first a ray and then rotate that ray. So I'm going to draw some random ray out in space, somewhere like over here, and then I'm going to rotate it. So that just means I'm going to kind of pick it up, rotate it about the endpoint, and then stop. Now, in doing that, I'm going to create a lot of new things, some new terms. Where I start, where I'm initiating this process, we call that the initial side. I'm going to pick up that ray and I'm going to rotate it. Let's go this direction, I suppose. And where I stop, where I terminate, we call that the terminal side. So I started with this ray, I kind of picked it up and rotated it and stopped here. It also created not an end point, but now I have the vertex of an angle. And we created this red angle. Now, the direction was very important as well. A clockwise rotation creates a negative angle. So when you look at a clock and you see the second hand tick around, it's going in a negative direction. We drew this counterclockwise, so I drew a positive angle. All right, so we've got this angle now. So I started off with some sort of initial ray. Just pretend there's an arrow up here. And then I said I would like to rotate this and then stop. And then that created the angle on the inside. All right. So angle sitting right there. All right, now I'm ready to give you a definition, something we call a central angle. Central angle. Now, central should hopefully spark some sort of center. So this is some angle dealing with a center. And in this case, we're dealing with the center of a circle. So a central angle is just one where the vertex happens to be the center of a circle. An angle with the center of the angle of the circle, sorry, an angle with the center of a circle as its vertex. See if that makes sense. An angle with the center of the circle as its vertex. Yeah, perfect. So I'm going to draw now a central angle, and that just simply means I've got some sort of circle, and the center of that circle just happens to be the vertex of an angle. So I'm going to draw an angle. Here's my random ray. Maybe that's my initial ray, I don't know. And I draw my angle rotating around, and maybe I stop right here. So I'm drawing that same ray rotated. And in order to talk about this angle, let's give it some letters. Let's call this, where the ray intercepts the circle here, I'll call that A. I'll call this other intersection C, and I'll call the vertex capital O. Not 0, but O. That's a common practice. Alright, so angle AOC is a central angle. The vertex of that angle just happens to line up with the center of a circle, or maybe I did that on purpose. We call that a central angle. Oh, some more denotion. You may remember. If I want to talk about that red angle, the way we denote angles is with this little like sideways symbol. So this is angle AOC. It kind of looks like the greater than symbol. But in this case, angle AOC. And then the order of the letters do not matter. So it's also angle COA. Those both refer to this red angle in here, AOC, COA, and even angle O. Angle O, this center angle, is this red angle in here. Now, there's this other angle out there in this. There's another central angle here. I'll draw it in blue. I'm not talking about this blue angle. That is also a central angle. But when I denote AOC, the central angle kind of refers to the smaller of the two. So because the red is a little smaller than the blue angle, then the red one is angle AOC. That's the one I'm talking about. All right. Let me kind of move on. Central angle. Now, we can use central angles to talk about the measure of a circle. What I mean by that? The measure of a central angle actually equals the measure of its intercepted arc. Intercepted arc. Before I continue, let me make sure that makes sense. So notice how the red angle here, it kind of cuts away the circumference of the circle. Like I had this beautiful circumference, but the angle kind of cuts it in these two places. So it kind of separates this part of the circumference out. So it's kind of like it's intersecting it. We're cutting it out. So that's what I'm talking about here. All right. If that angle in there measures a certain degree, then it's going to equal the measure of that intercepted arc. So if that red angle, maybe it looks like 135 degrees. If that measures 135 degrees, then the arc, or that intercepted arc, also measures 135 degrees. So I'm going to put in my notes here. If a central angle cuts away in degrees of a circle, then the angle measures in degrees. So both ways. If the angle measures in degrees, then that arc measures in degrees. If that arc measures in degrees, then the angle measures in degrees. So I'm now very curious. If I have a circle, I'd like to kind of maybe measure the arc of a circle. So a circle maybe we're all familiar with would be a clock, like maybe in your office setting or at your school. So I'm going to draw a clock on here, and maybe I'm curious about the arc length, that distance between the 1 o'clock and the 2 o'clock position. So let's find the measure between 1 and 2 on clock. So I'm going to draw my clock here the best I can. Due north is 12. I've got a 3 o'clock, 6 and 9. But I'm really curious about 1 and 2. So I'm going to go ahead and cut those into nice 3 equal slices, 1, 2, 3, between 12 and 3. And I'm real curious about the distance between 1 and 2. In fact, let me put some letters on here and talk about it that way. Let's find arc AB. So here's some notation you may remember from geometry. We've got AB and this little rainbow symbol. That's arc. So let's let 1 be A, 2 be B. And arc 1, 2 is this red arc right here. I'm going to find that measure. I want to find that distance. If I just bust out a ruler, that measures straightness, not curvature. So I guess I could get crafty and get some string and kind of like lay it about the clock, cut the string, and then pull it taut or straight, and then measure it. But I think I'll use this central angle idea. I want to know the measure of that arc, and one measure would be the measure of the central angle. So this distance here is equal to this angle here, this central angle. Okay, I think I could find the angle of this, or the degree of this angle, the measure of that angle. I know there are, in total of a circle, there's 360 degrees. So I'll start there. There are 360 degrees in a circle, and we've taken this circle and we've cut it up into 12 equal parts, 12 hours. So there are 12 hours in a clock, or in this circle. And I'll just divide. 360 degrees divided by 12, that's going to give me 30 degrees per 1 hour. So there are 30 degrees sitting right there. So if I can find the measure of this central angle, and it measures 30 degrees, then I can say that the piece of the circumference that it cuts away, this intercepted arc, will also measure 30 degrees. We may have been more comfortable with like inches or centimeters, but this is another way to talk about distance between, or this curvature of the circle. That arc measures 30 degrees because that central angle also measures 30 degrees. All right. Let's move on to, something we call standard position. We use this a lot in this class, where I've got one branch of math, algebra, and this other branch, geometry, and I kind of want to mesh them together. So later in the class, we'll take something like an ellipse, and we want to talk about it. So what we do is we just kind of pick it up and we put it on the Cartesian plane. So we're no longer talking about geometry, we're talking about x's and y's. That process is called like rewriting it in a standard position. I'm going to do that with an angle. I have an angle flying around in space, something like this. And in order to talk about it, I'm going to put it in standard position. In fact, this angle, if I asked you to tell me if it was positive or negative, without knowing what's the initial side and what's the terminal side, you're not quite sure. But if I were to put it in a standard position, maybe we could talk about it. So an angle in standard position has its initial side on the positive x-axis of a Cartesian plane. And its vertex will line up with the origin, the point 0, 0. So now all of a sudden I can start talking about, like we can maybe talk about this angle here. Let's do this angle here. Yeah. All right, so I've got this angle flying around in space, and at this moment we're not sure if it's positive or negative or what's going on. But if I were able to put it in a standard position, something like this, I'm taking the initial side and putting it on the positive x-axis, so left and right. This is now the origin of a Cartesian plane, and then the terminal side just falls where it falls. So I'm going to draw that angle in standard position. That is, I'm going to draw a Cartesian plane, the x and y rectangular coordinate system, and I'm going to put the vertex of the angle at the origin. Its initial side is on the positive x-axis, not the negative, but the positive. And then the terminal side just kind of falls wherever it falls. So now I can say, okay, yeah, that was probably a positive angle. And it even looks like 120, 135 degrees. I can, because it's in quadrant 2, I can say it's bigger than 90 degrees, so it's obtuse. So we can talk about it better if we put an angle in standard position. And in fact, I have you do this in the homework. Just the first starting off questions is just drawing certain angles in standard position. So here's an example of that. Let's do something hard. Negative 210 degrees in what we call standard position. Standard position. So if you want to pause the video and give it a try and then compare your answer to mine, that'd be cool. All right, the way I'm going to handle this is standard position to me means I need the Cartesian plane. So I'm going to start there. I'm going to draw an x and y axis. Now when I first introduced angles, I talked about negative angles. Negative angles go clockwise. So I know if an angle is in standard position, the vertex is at the origin, it has an initial side pointing due east or due to the right on the x-axis. And if I want to create a negative angle, I need to go clockwise. Okay, well I need to go 210. Well, what's that? Okay. Well I know this forms like a right angle or is 90 degrees. Another 90 degrees is 180. I'm almost there. Oh yeah, the angle measure of a straight line is 180. Now I just need 30 more degrees to get to 210. Right now I have a negative 180 degrees. Oh, 30 degrees we talked about earlier. Every 30 degrees is 1 hour on the clock. So if you want to think about a clock to help you figure this out, a 9 would go there, a 12 would go there. You would bust this up into 3 equivalent sections. That's 90 degrees cut into thirds. So 30 degrees, 30 degrees, 30 degrees. I just need one of those. Let's see if I can put an arrow on there to show my direction. And this angle is negative 210 degrees. So when you're drawing angles in standard position, you start on the positive x-axis. Positive angles go counterclockwise. Negative angles go clockwise. And then just use the fact that you know what 30 degrees looks like, you know what 90 degrees looks like, and then do your best to draw that angle. All right, let's move on. Let's go on to another vocabulary term. I need to talk about something called coterminal angles. Coterminal angles. Well, I bet it's an angle. Co in English means like together or same. So these are just angles that have the same terminal side. And then in standard position. So I've got 2 angles flying around in space. When I put them in standard position, they have the same terminal side. They're both pointing in the same direction. So maybe let's use that same negative 210 degrees, and let's find a coterminal angle to that. Let's see a little example here. Example, maybe I'll ask you this on your homework or something. Find a coterminal angle to that negative 210 degrees that we just talked about. So we know what that looks like. I want to find an angle that in standard position will have an initial side and a terminal side. And that terminal side happens to be the same spot. Let me think of one. How about if I went this other direction? If I started here and went 90 plus 60, that would get me to that same terminal side. 90 plus 60, that's 150 degrees. If I were to draw 150 degrees in standard position, it would look exactly like this. So therefore, they are coterminal angles. All right. Can you think of another one? A coterminal angle to negative 210 degrees and 150 degrees. Maybe I took that 150 and I just kept going. So I'm going to start on the positive x-axis, going in a positive direction. I'm going to make one full rotation about the circle, and then keep going. That's a giant angle. But that is, I started on the positive x-axis, and I went in a positive direction, 360 plus 150. And that's how we can find coterminal angles. We can add or subtract 360 degrees. We find coterminal angles by adding or subtracting 360 degrees. Basically, just a revolution around the clock. So the first one we did visually, negative 210 degrees plus 360 degrees. That's how we got that blue 150 degrees. If I did 150 degrees and added another 360 degrees, well, that looks like 510 degrees. So 510 degrees is also coterminal to 150 and negative 210. We could also subtract negative 210 degrees minus 360. That's going to give us negative 570 degrees. That's another coterminal angle. So a question I could ask you, something like this. Find the least positive angle in standard position that is coterminal to 765 degrees. Oh my goodness. All right. 765 degrees. I have no idea what that looks like. It's really, really big. It goes around the circle at least 2 times. All right. And I want to find the least positive coterminal angle. Well, that just means I want to make this angle smaller. So I'm going to subtract 360 to get it smaller. But I don't want to go too far. I don't want to make it a negative number. So I think what I'll just do is take my 765 and I'll just chip away at it 360 degrees at a time. 765 is coterminal to 405. 405 is coterminal to, hard math, 45 degrees. If I go any further, it'll go into the negatives. I don't want that. I want the least positive. So 45 is smaller than 405. So I prefer this one, but I can't go any smaller. All right. Now this whole time we've been talking about degrees, and the title of this video is angle measure. That's how we're measuring the angles are in degrees. And we're very comfortable. We know that like what 90 degrees looks like. We know 1 degree would be this tiny angle, and we all know what that looks like. And that's worked for us for a long time. It's a great way to measure and talk about angles. But when we move into the calculus, when we move into like bigger sciences, we need a more exact definition of what a degree is. So we're going to switch over to something called radian measure, or radians. Okay. The definition of a radian is quite confusing at first, but it's really simple and kind of elegant as well. Okay, the radian measure, so we're talking about angles here. The radian measure of an angle in standard position equals the length of the intercepted arc which you know what that is, divided by the radius. So this is like where I was trying to get to in this video. I want to get to radian measure, how we talk about the measurement of angles. But before I could, you see I had to talk about standard position, intercepted arc. Now that means we've got a circle and the angle is it's like a central angle. The vertex of the angle is the center of that circle. And it's in the standard position, so it's all come together for this definition. All right. So words may be scary. Let's get a picture on here and show how nice this is. I'm going to draw a circle. That standard position implies Cartesian plane. I'm going to just kind of draw it lightly. I don't want to get into my way, but we are in standard position. So the vertex of our angle is at the center of a circle because of the arc, and it's also at the origin of the Cartesian plane. And if I want to talk about the angle measure, it's the intercepted arc divided by the radius. Okay, well, let's put some letters up here, some variables. Let's call the intercepted arc, I'm underlining it in a red color. Let's call that S. And let me just put an intercepted arc on here. So let me just draw a ray somewhere over here. Of course, it has the initial ray. And we've created this arc. It's been cut away. And I'm going to call that S. Well, the measure of this angle in here will equal that arc length divided by the radius of the circle. So I'm just going to label the radius. I'll call this R, little r. That would be from the vertex to right there where the ray intercepts the circle. I have another radius over there, but this is convenient. And because we're talking about radian measure, I'm going to switch over to a Greek letter, theta. And maybe up here where I underlined radian measure, I'll say we're talking about the Greek letter theta. That's T-H-E-T-A, theta. In algebra, we use letters for variables like x and y. For radians, we use the Greek alphabet. So you'll see theta, alpha, and beta are also common. Those are just placeholders for the radian measure of a circle. Right now I'm using theta. That's the most common. Like x is for algebra, theta is for radians. Okay, so then my definition here just says the radian measure will equal the intercepted arc divided by the radius. That's the definition of radian measure. All right. So that's great and all, but I have no idea what 1 radian looks like. I have no idea how many radians this is. In degree land, I could tell you, oh, it's obtuse. Maybe it's 135 degrees. And so I know I've got degrees like in my brain. But now I'm trying to switch over to radians. So let's see. What do I know about radians? What do I know about angle measure, arc length measure? Oh, we did say earlier this arc length would be equal to that measurement in here. So I think what I know about circles is their circumference. I know the circumference of any circle is 2 pi r. Let me just kind of write that down. If I have a circle, I know that the circumference of the circle, that is, if I were to draw an angle that, I want to call 360 degrees, that cuts away the entire circle. So that's my initial side and my terminal side. It cuts away the entire circle. So my S in this circle is all of it. Well, the circumference of a circle is 2 pi r. And then the r is just the radius of this circle. So this circle has a radius of r. So if I just cut away the entire circle, then by definition, theta is equal to the intercepted arc length, which is all of it, 2 pi r, divided by the radius. Oh, well, division, the radius divided by itself, this is going to reduce. And I'm going to have theta, the radian measure of that angle, is equal to 2 pi. So I know in degrees there are 360 degrees in a circle. I now know in radians there are 2 pi radians in the entirety of a circle. That's going to be convenient. 2 pi radians is equal to 360 degrees. So this equality is going to be very helpful when converting from degrees to radians and radians to degrees. I know what 360 degrees looks like. I now know what 2 pi radians looks like. Pi is that number, like about 3.14. So if you want to grossly round that down to 3, 2 times 3, so 6 radians, kind of. That's the rounding down. 6 radians is about 360 degrees. So radians are much bigger than degrees. And in fact, I'm going to take this equality and make it a little bit nicer. I'm going to divide both sides by 2. So pi radians is equal to 180 degrees. There are 180 degrees in a line. There are pi radians in a line. Okay. I'm going to use this equality to start some conversions. So some of your homework problems will be to take a degree and convert to radians, and vice versa. Let's get started. Pi radians equals 180 degrees. Pi radians equals 180 degrees. Pi radians equals 180 degrees. All right, so to convert degrees to radians, we simply multiply the degree by pi over 180. Radians. Okay, so we just said earlier pi radians is equal to 180 degrees, so they're equal. That's like saying 5 equals 5. Those are 5s. 5 equals 5. So if you take 5 and divide by 5, then that's just 1. So it's legal to multiply by pi over 180 because this is just 1. You can multiply by 1. So that's exactly what we're going to do. Here's an example. Let's convert 36 degrees to radians. You can pause the video and try it yourself. I'm going to take 36 degrees and I'm going to multiply by this relationship, pi over 180. All right. I wish that radians was kind of written up there. This is pi over 180. Again, I'm just multiplying by 1, so I'm not changing the value, I'm just changing what it looks like. If you've done, like in a chemistry course, you do a lot of unit conversion. Notice I'm putting the degree that I'm trying to get rid of in the denominator. So when I do the division, the degrees will cancel out or reduce out. And I'm introducing radians. I'm multiplying by pi 80 radians. So I'm introducing the radians. Well, that's a nice, pretty conversion. That goes in there 5 times. So you simplify that out, and you're going to have pi fifths radians. Now, when we don't write a unit we're understood to be in radians. So if you see a rad or r, that helps us know we're in radians. But if I just simply write pi fifths, then I know we're in radians. Whereas if I wrote down earlier like 360, I'm assuming that's radians until you put the degrees symbol. That's 360 degrees. There's no real universal symbol for radians. It's just kind of understood. But for today's lecture, I'm just going to write radians or rad just to let us know. We went from degrees to radians. So 360 degrees is equivalent to pi fifths radians. Remember pi is about 3, so this is about 3 fifths. So it's not quite 1 radian. 360 or 36 degrees is not quite 1 radian. It's pi fifths radian. All right. So in homework, we may do some of that. Now, let's do the other direction. Let's take a radian and convert it to degrees. Let's do something like, oh, I don't know, negative 30 degrees. Negative 30 degrees, that's pointing down into quadrant 4. I know what that kind of looks like. That would be the 4 on a clock, that 4 o'clock position. But I want to take that negative 30 degrees and convert it to radians. So in this case, I'm going to do the opposite. I'm going to multiply again, but this time by 180 degrees over pi radians. Oh, this is degrees again. Oh my gosh. I need a radian. Well, let's just continue this problem. So I'm doing degrees. I did not switch over to radians like I wanted to. But let's just do this problem real quick. And we already know this, I think. I'll take that negative 30 degrees, multiply by pi over 180. The zeros nicely reduced. The degrees symbols reduced. 3 goes into 18 6 times. So this is a negative pi 6. So negative 30 degrees is equal to or equivalent to negative pi 6 radians. Notice I didn't write the radians, it's just understood. We're now in radians. All right, let's do the other way. So to convert radians to degrees, we're going to multiply by that same equality, but this time I want the radians to go away. So I'm going to put the radians in the denominator, and I'm going to introduce the degrees in the numerator. 180 degrees over pi. All right, for example, let's take a common radian, something like 4 pi thirds, and let's see what that is in degrees. Like I don't know what this looks like, but maybe if I can convert it to degrees, I'll know what it looks like. So I'm going to multiply, again by that same equality. I'm going to put the pi radians down below, 180 up top. The pi's will reduce, meaning the radians have reduced. I have introduced degrees. You could do 4 times 180. I think it would be probably a little easier to go ahead and divide the 3 into the 180. That's a pretty 60 degrees. So I'm going to have 4 times 60 degrees. I know double 60 is 120. Double it again. That should be 240. So 4 pi thirds radians is equivalent to 240 degrees. All right, so in the homework, you'll convert back and forth. Do that enough times that you're comfortable with it, and hopefully get faster and faster at it. All right, one last problem I'd like to talk about, and it uses something called the arc length theorem, which I claim you already know. You know the definition of radian measure. Tell it to me. What is radian measure equal to? How's it defined? Well, yeah, the arc length, the intercepted arc length divided by the radius of that circle. If I just take this equation and solve for s, that arc length, I'm going to multiply both sides of the equation by r. S, or that arc length, is equal to theta times r theta, theta r. In this form, we call it the arc length theorem. Up here, this is just the definition of radian. But maybe I have this on my notes, so now maybe I can do some new problems. Maybe I want to find some measurements of some different arcs. Let's say I look at my globe, and I'm looking at the different parallels, and I notice that Evans Island, Alaska sits on the 60th parallel. Okay, I'm going to draw a picture of the Earth. So Earth is for most part circular in 2 dimensions. There's my Earth. So across the center of the Earth we have the equator. And due north would be the North Pole. So that sits at the 90th parallel. But I noticed that Evans Island, Alaska, sits at about the 60th parallel. And what that means is, if I were to draw a ray out to Evans Island, then the angle from the equator to that ray is 60 degrees. All right, now what I would like to do is use the arc length theorem to find S. So I'm really curious in the distance between Evans Island and North Pole. So I'm trying to find S here. I want to know, if I'm going to make that trek, what's that distance? And I want to know, with the curvature of the Earth, what's going on here. All right, one way is to use this arc length theorem, which simply takes the theta and multiplies by the radius. Now if you ask Alexa or Google what the radius of the Earth is, you may get different approximations. Let's use 3,950 miles. So if you see a problem like this in the homework, you may not use 3,950. Depending on your resource, you may look that up and get a different number, but that's okay. We're just going to approximate this distance the best we can. Okay, so if I want to find S, I need to take the radius and multiply it by that theta. Well, that theta is the angle between Evans Island and the North Pole. Okay, I think I can do this. S would be equal to 3,950-ish miles times that angle in there. Well, what does that angle measure? If you said 30 degrees, you're only half right. Remember that theta came from the radian definition. So we're not talking about degrees here, we're talking about radians. So I'm going to have to first convert 30 degrees to radians. All right. Evans Island sits at the 60th parallel, making this angle 60 degrees. I'm more concerned with this angle, which makes a 90-degree relationship with the North Pole. So this is 30 degrees left over, but I need that in radians. So I think I've done this already. 30 degrees times, put the degrees down below to get rid of them, introduce the radians up top. 30 goes into 186 times. So this is pi 6 radians. 30 degrees is equivalent to pi 6 radians. So I'm going to multiply by my theta, pi 6. All right. I could probably do some reduction. They're both even, but I acknowledge that pi is going to be some approximation here. So I think I'll just bust out a calculator to finish this off. Oops, looks like I worked ahead. I've got 3950 times pi up top, and I need to divide all that by 6. So I get about 2,068 miles. Something close to that. 2,068. All right, so again, you may see some like earth problems in the homework. This is kind of the way I would work those problems. So I hope this video helped with this new definition or this new way to talk about angle measure, radians. And we're going to use that terminology we've talked about in this lecture to go on to the next lecture where we start to talk about the trig functions. See you next time.